Good morning. I'm Nancy Marlin, the University Provost, and I'm delighted, on behalf of San Diego State University, I'm delighted to welcome all of you to this first lecture event of the 2005 Kyoto Laureate Symposium. This symposium, as I think most of you are aware from the program, is a three-day celebration of the lives and works of those receiving the Kyoto Prize, Japan's highest private award for lifetime achievement, awarded annually to individuals and groups worldwide. In hosting this symposium jointly with the University of San Diego and the University of California, San Diego, we hope to provide an opportunity for an international audience to learn about the current Kyoto Prize laureates and to contemplate the relationship between their remarkable accomplishments and the common quest for peace and harmony in our world. Before we turn to today's speaker, Alan Kay, the 2004 Kyoto Prize laureate in advanced technology, I have the pleasure of introducing some of the esteemed guests who are with us today to share this occasion. We have with us the three 2004 Kyoto Prize laureates, Dr. Alan Kay for Advanced Technology, Dr. Alfred Knudson for Basic Sciences, and Professor Jurgen Habermas for Arts and Philosophy. Would the three of you please stand and be recognized? We also are extremely honored to have the founder and chairman emeritus of Kyocera Corporation, advisor to KDDI Corporation, the president of Japan's Inamori Foundation, which awards the Kyoto Prize, Dr. Hazuo Inamori. There are also several directors of the Inamori Foundation with us, and as I call each name, I would ask that they stand and that applause be withheld until all have been introduced. Dr. Hiroro Imura, Dr. Shinji Fukukura, Mr. Toyomi Inamori, Mr. Mikio Okono, Mr. Asa Jonishi. Leading our symposium events from the community, we have with us Mr. Malin Burnham, chairman of the San Diego's Kyoto Symposium organization, and also Mr. Tom Fatt, who co-chaired with Malin Burnham last night's wonderful Kyoto Symposium Gala. And finally, I think we all are the beneficiaries of the organizational committee here at San Diego State University, and especially the wonderful work of Miss Kristen Dowd. Kristen, where did you go? She's in the back. Thank you. Today, Madam Kaneko Bishop would like to honor this important occasion through a symbolic flower arrangement. Madam Bishop is professor of the Omoko Senkei School of Tea. The Japanese tea ceremony is a combined art in which flower arranging is an integral component. She has chosen the container in the form of a circle to represent the universities, and there will be flower stems inserted. The first flower stem will be inserted by Dr. Inamori for his great vision and philosophy. I will insert the second stem on behalf of San Diego State University to symbolize wisdom and guidance. The third flower stem will be inserted by Dr. Alan Kay for his knowledge and contribution to humanity. And the fourth stem will be inserted by Dean Thomas Scott for his leadership and inspiration. Madam Bishop will then add water to symbolize this symbolic arrangement and nurture it.
I have chosen a container in the form of a circle. The first flower stem will be inserted by Dr. Kazuo Inaba for his great vision. Stem will be inserted by Provost and Vice President Nancy Marlin for her wisdom and guidance. By Dr. Alan Curtis K. for his knowledge and contribution to society. Fourth will be this lead. Inserted by Dean Thomas Scott for his leadership and inspiration. Again, I'll add water to nurse this symbolic arrangement. We are most honored to participate in this morning's memorable occasion. I truly believe that the contribution of these dedicated people will make a better life for all mankind. 心に銘記すべき本日の催しに参加させていただきましたことを大変光栄に存じます。また、こうした方々と献身により世界の人々の人生が豊かになりますことを信じます。ありがとうございました。 My assistant today, Hiroko Shidensky, she's the instructor for Soviet School of Ikebana and the director of the San Diego chapter. Also, Miki Haneda, she's this university's graduate student.
Now, to give you some perspective on the nature of the award that Alan Kay recently received, we will show a short video introducing the Kyoto Prize.
Foundation is proud to present the Kyoto Prizes each November 10th in Kyoto, Japan. The Kyoto Prizes are presented to individuals and groups worldwide whose work has shown a significant contribution to the betterment of society and mankind. Kyoto Prizes recognize 3 categories of human achievement: advanced technology, basic sciences, and arts and philosophy. The Kyoto Prizes consist of academic honors, a 20-karat gold Kyoto Prize medal, and a cash gift totaling 50 million yen, about $450,000 per category. Dr. Kazuo Inamori's belief that mankind's future depends on the balance of science, technology, and the human spirit is reflected in the Kyoto Prizes, which promote this balanced development of science and humanity. They are designed to recognize outstanding achievers globally and to inspire people to even greater achievements. The Kyoto Prize ceremonies have long been attended by members of Japan's imperial family. The audience includes international dignitaries and elite representatives of academia, science, technology, the arts, business, and government.
Permit me now to convey to you a message from George W. Bush, President of the United States of America.
Each year, global heads of state offer their thanks and congratulations to the Kyoto Prize laureates for their important contributions to society. These leaders' recognition and support underscore the importance of balancing technology and humanity, especially as we face the challenges of the new millennium. Kyoto Prize laureates are selected from specific fields within the 3 categories. The Inamori Foundation's rigorous nomination process ensures unbiased consideration of the nominees, and the laureates are then selected with the approval of the Foundation's Board of Directors. The Inamori Foundation was created in 1984 with a personal endowment of 20 billion yen from Dr. Kazuo Inamori. Dr. Inamori is the founder of Kyocera Corporation, a multi-billion-dollar global enterprise that he established with the equivalent of just $10,000 in 1959. Dr. Inamori created the foundation in reflection of his philosophy. He has long said that human beings have no higher calling than to strive for the greater good of humankind and all the world. With Dr. Inamori's subsequent donations, the Foundation's net assets by 2004 total more than 64 billion yen, or about $600 million. For 20 years, the Foundation has awarded the Kyoto Prizes to recognize outstanding contributions to scientific progress, cultural advancement, and human achievement. The Kyoto Prize laureates are people, completely devoted to their work. They hold a deep reverence for the human spirit. They've dedicated their lives, often with little recognition or encouragement, to creative work that benefits all humankind. Their continued devotion to learning, to excellence, and their outstanding accomplishments for the common good establish them as truly deserving of these awards. To build a future based on a balance between science, technology, and the human spirit. to encourage balanced development of mankind's cognitive and spiritual sides. To help ensure peace and prosperity, we honor our laureates for their extraordinary efforts and outstanding contributions to humanity. This is the mission of the Kyoto Prize.
I'm Thomas Scott, Dean of the College of Sciences at San Diego State University. December 6th, 1962 was the last day of classes in the first semester that I spent at a rarefied Eastern university, and the time when the semester's work really began. The tradition was to have a 12-week semester followed by a 2-week reading period during which we were given an independent assignment in each of our 5 classes to carry out during that ensuing 2 weeks in anticipation for the final exams that came in January. And the assignment that I was given in my mathematics class was to write a computer program in Fortran that could be used to calculate the 4th root of my university store number, what would correspond to a red ID today, which seemed a rather daunting task. The 12 of us in the class were taken somewhat ceremoniously to be introduced to the awesome adjudicator of whether or not we had met with success in our attempts, and this was an IBM, I believe, 7090, though I've probably repressed the numbers and mangled them in some way. And it was a hallowed occasion. The computer occupied 1,000 cubic feet in its own larger room. It was all encased in glass, temperature controlled, humidity controlled, all set on springs to guard against the violent upheavals of central New Jersey. And we were told that it had cost the university $3 million, which was about the price of a major building in those days. We all pressed our teenage ears against the glass and listened to the humming of this mechanical mind. And our instructor said to us, "Gentlemen," it was an all-male university at that time, "Gentlemen," in a tone that he had, of respect that he had never shown for any human being during the semester, "this is the future of computing." He didn't know that Alan Kay was on the loose at that time. With the breeze of Moore's Law at his back, Alan set off to create a computer that you didn't have to have an appointment to meet, a computer that you could take with you, a personal computer. He unveiled his concept as the Dynabook in 1972, such a 70s name. This was followed by the Alto, as in Palo Alto Research Center, which defined much of the progress that was subsequently made in the production of the Macintosh computer and the Windows operating system. Alan helped create a high-speed Ethernet over which computers could be connected in local area networks, which then, on steroids, became the Internet. The Mac, Windows, the Internet, this was truly a paradigm shift, such as the world sees only occasionally. Several weeks ago, 4 of us from San Diego State drove up to Glendale, where Alan's laboratory is, to visit this shifter of paradigms. We discovered a casual, sociable, intellectually vibrant, thoughtfully opinionated man who seemed not so much to notice all that he had accomplished, but rather to concentrate on what he still had to do. To use computing power as an educational tool, always in the service of intellect, in the service of imagination. As Alan noted during our discussions, you get about 30,000 days. You've got to use them well. Alan's only used perhaps not even 24,000 of his, and yet the world is already a better place. I'm honored to introduce Alan Kay, whose Kyoto lecture title has been before you for nearly half an hour now, Understanding Powerful Ideas and How Computers Can Help.
Thank you very much. It's wonderful how stories improve in the telling. 10 years from now, I will have reached back and be credited with everything that Babbage did as well. But actually, people in our field work in a community, and so the citations for awards in our field are really a tacit way of acknowledging many, many people who work together. And our field is a practical field in that, in theory, you're supposed to build your claims. And one person doesn't get to build very many claims. And so the unusual thing about technology is the way it sort of combines ideas about the real world that we think of as having to do with science and ideas from the world of art and story, which we think of as being more internal. In fact, the root of the Greek word for technology means things that people make. And some of the ancient Greeks thought of it as being the same word with the same meaning as episteme, which is loosely translated as having to do with knowledge. And other Greek writers and philosophers thought of the techne as being rather different, as being having to do with practical arts and so forth. So what I'd like to do, as soon as we can get Bill to cooperate here, is to talk a little bit about why we might be interested in computers beyond the simple practicalities of recreating the world of physical representations in the world of bits, and recreating the world of accounting in the worlds of bits. And actually, the most important idea is that the computers actually bring something new to the table, and it's not easy to explain. At least I haven't found it easy to explain just what that is. So the Kyoto Prize gave an opportunity to come up with many lectures. And so each lecture I've tried to take a slightly different slant on this to explain why I think this is vitally important for the future, especially of children and the human race. So my conversion went from having worked on this desktop computer with my friend Ed Cheadle, which we thought of as being like a kind of advanced tool, or maybe even a vehicle like a car for doing things with information. And because we intended it to be a personal computer for professionals, millions of professionals, we started looking around at people who were not computer professionals, but were professionals in other fields. And during that process, I ran into Seymour Papert, who was actually working with children about age 12 in those days. And Papert was a mathematician, and my background was in mathematics and biology. And I saw Papert do something just astounding on that visit in 1968. And he was trying to get children to draw a circle using the logo of turtle, which is a little beast that ran around the floor and had a magic marker and a butcher paper. the mark, so the children can steer it by the programs. So Seymour challenged them to come up with a circle. And of course, to a high school student, a circle analytically is x squared plus y squared equals r squared. And it's interesting to talk to most high school students and their teachers to see if they actually understand what that actually means. And in fact, in America, most people have no idea what x squared plus y squared equals r squared, even though that's the official doctrine of the analytic geometry of the circle. But after being a real mathematician, there are lots of ways of thinking about a circle. And in fact, in antiquity, the circle did not have to have Cartesian coordinates. And in fact, the Greeks weren't quite sure where zero was, maybe at the center of the earth, but maybe somewhere else. But they just didn't make reference to some coordinate system to draw a circle in the sand. And so what Packer did was to get them to close their eyes and make a circle with their body. When they're about halfway around, he asked the children, well, what are you doing? And the child would say, well, I'm going a little, I'm turning a little, over and over. And in the language that Packard helped originate, called Logo, going a little is forward 5, turning a little is turn 5, over and over is repeat. And if you tell the turtle to do that with the pen down, why, it will draw a circle. Notice it draws it without reference to where the center might be. So it's not even like using a compass. It's using the fact that a circle is a curve that has constant curvature. And this form of mathematics is called differential geometry. And it is one of the main forms of mathematics that is used in science today, differential geometry of vectors. And Pappert's genius was to realize that this thing that is so easy to do on a computer actually is also in the psychological world of children. In fact, this mathematics is much easier for children to learn than the arithmetic we tried to teach them in school, and it's much more powerful. So it's actually quite possible to teach children the powerful ideas of the calculus as long as they have a computer to carry out the implications of that. So that was one of the greatest shocks I've ever had in my life, because my image of what the computer was went completely from thinking of it as a tool or a vehicle to something cosmic, something more like the printing press, or something like the invention of science itself, a new way of looking at things that could have a tremendous positive benefit on the kinds of thinking that children are able to do as they grow up. And somewhat akin to learning of language, the epistemological stance that you take on as a child, for most children, is pretty much fixed by around age 7. So what if it were possible to give children a much more modern stance on knowledge and the universe at a much earlier age? Would they be very different as high schoolers, and would they be very different as adults? Would they be less like a cave person with a briefcase as adults, and would they actually have some sense of the various uses of reason and be able to reason about reason? So all of those things flashed through my mind, and on the plane going back to Utah, I had this image of children using a personal computer, but of course not on the desk, because children are mobile. So they had to have something like a notebook. And I had this idea that children could actually learn powerful ideas by making their own models in this new form of mathematics. And for them, many of these models would be in the form of games, but games about reality.
Alan, you use the mic.
Well, I am using the mic.
It's not
It's not working.
Well,
So that was going to cramp me.
you can take it off.
Well, I don't want to do that. I know I don't want to do that. So then we got the chance of a lifetime to go with a bunch of wonderful colleagues, and one of them is here tonight, Ted Kaler. Raise your hand over there. Hey, Ted. Many, many years ago, but about 24 people, not me, 24 of us together made a lot of the fundamental inventions in personal computing today. It was actually rather easy, and it was a heck of a lot of fun. It was easy in part because the technology had turned an important corner right around 1971. It was easy partly because this group was supremely well set up for doing it, and the funding was perfect in that the scientists were allowed to follow their own noses on these projects and were able to work well with each other and had a strong sense of destiny. So that was a lot of fun, but the interesting question is, what are, of all of the practical and mundane aims we could have for this new set of amplifiers, what are some of the more interesting ones? And the thing I thought would be really interesting was if we gave this machine to children with a way of making things on it, it'd be very interesting to see if we could actually get them not just to learn mathematics, which is relatively easy, but to learn science, which is much harder because of partly because of the 3 pounds of messed up porridge we have between our ears that persists in seeing the world not from the standpoint of reality, but from the standpoint of ourselves as human beings. And so that became an interesting challenge. And one of my favorite lines about science is Niels Bohr, who said, "Science is not there to tell us about the universe, but to tell us how to talk about the universe." In other words, as human beings, we have representation systems physically in our brain, and we have invented various kinds of languages and ways of using that we use to reason with, but those have no necessary connection with what's out there. And so science is actually a relationship between what's out there and what we can talk about and reason about. And you can think of this as a different way of critiquing the notion of pure reason. I also like Professor Habermas's much more subtle approach. So I'm hoping that you will all go to his lecture, because the tricky thing about learning how to reason a little is it leads people to think that they can reason a lot. And even the Greeks got caught up with this. They thought for a long time that God must be a mathematician because math was so neat. And therefore you should be able to deduce the physical structure of the universe by just using mathematical reasoning. It turned out not to be the case at all, and yet math has been tremendously useful in representing ideas as we find them out. Another way of looking at this is Dr. Inamori's approach, which we heard the other day in the business lunch. And to paraphrase what he said, the more talent, ability, and knowledge we have, the more careful control is needed, and he says this control is what we call character. So character development is critical in any of the 100,000 years that humans have been on Earth, but it's absolutely critical now that we're much more powerful than a cave person with a club. I think of science as something that is philosophically interesting. In fact, it is a part of philosophy because of this peculiar self-questioning nature it has about its own methods and the fact that messy human beings are involved. So somehow science tries to find a way of saying reasonable things using a set of materials, including us, that are not terribly reasonable. And we should use that approach, I believe, much more in dealing with social situations and understanding ourselves. So here's an example of something interesting about real human beings. This was a visit to a different East Coast university, Harvard University, which prides itself on being a top place. Right after graduation about 10 years ago, NSF took a camera person and an interviewer and ran around interviewing the graduating seniors, their parents, and some professors. And here's what happened.
To test how a lifetime of education affects our understanding of science, we asked these recent graduates some simple questions in astronomy. Consider, for example, that the causes of the seasons is a topic taught in every standard curriculum.
Okay, I think the seasons happen because as the Earth travels around the sun, it gets nearer to the sun, which produces warmer weather, and gets farther away, which produces colder weather, and hence the seasons.
How hot it is or how cold it is at any given time of the year has to do with the closeness of the Earth to the sun during the seasonal periods.
The Earth goes around the sun, and it gets hotter when we get closer to the sun, and it gets colder when we get farther away from the sun.
Wow. These graduates, like many of us, think of the Earth's orbit as a highly exaggerated ellipse, even though the Earth's orbit is very nearly circular, with distance producing virtually no effect on the seasons. We carry with us the strong, incorrect belief that changing distance is responsible for the seasons.
I took physics, planetary motion, and relativity electromagnetic waves.
I've never really had a scientific background whatsoever, and I got through school without having it. I've gotten very far without having it.
I had quite a bit of science in high school, yeah, through physics, first year, and 2 years of chemistry.
Regardless of their science education, 21 of the 23 randomly selected students, faculty, and alumni of Harvard University revealed misconceptions when asked to explain either the seasons or the phases of the moon.
When it's further away from the sun, then it gets colder.
The Earth's position interferes with the reflection of the sun against the moon.
So does anybody recognize where his regalia is from? Harvard?
Mm-hmm. Yeah.
So this guy has probably never been off the quad. So now I think that people who are familiar with this know that this can be done randomly almost anywhere, and you get about the same results. I kept on waiting for NSF to ask the next obvious questions, but on this video they didn't. But a few weeks after I first saw this video, I was giving a talk over at UCLA and found out that my audience was mostly seniors and a few first-year graduate students, so I asked some of them to come out on the lawn after the talk so I could try these questions out on them. And I got about the same result. About 95% had severe misconceptions on one or both of the seasons and the phases of the moon. But of course, I got to ask the next obvious question. So let me ask the audience here, what is the next obvious question about the seasons that you would ask anybody? Yeah. So I asked them, I said, when it's winter up here in North America, what's the season down below, southern part of the Earth? And every single one of them said it was the opposite season. Every single one of them remembered that, but of course they had no idea why. And then there's this interesting process of about 20 seconds when they gradually realized that the opposite seasons answer completely contradicted their... But none of them were able to come up with that fact that they knew when they were answering the original question. And same thing, what about with the phases of the moon? What's the next obvious, what should we ask this professor as the next obvious question? This is a trickier one. So now a good one is to ask them, have you ever seen the sun and the moon in the sky at the same time? Have you? Has the moon sometimes been in phase? So if they're not at opposite ends of the horizon, the moon is always in phase. And again, the 20-second pause as they realize there's no pseudopod sticking up from the Earth that could be causing that shadow. So this is not a science problem. And we should be very happy because the NSF people actually would not have made this video if the kids had remembered the right answer. because that's all they're asked to do today. But so this is actually a thinking problem, because in both of these cases, the people who had misconceptions actually had a way of doing something about their misconception, which is they had a counterexample for their theory, and yet they couldn't find that counterexample. It was not in their set of heuristics for thinking about anything to search for counterexamples. So it's kind of interesting. But it's not unusual. In fact, it could not be more natural. So when anthropology first started studying differences of cultures, and then they started finding out that cultures underneath, the next level underneath the culture, had many, many similar characteristics. Every culture had a language. Every culture used stories as a way of thinking and communicating and remembering, and so forth. Many different things called cultural universals. And then there's also another collection of things that are not found universally among cultures around the world. So things like reading and writing, that's not built into us in any direct way. It had to be invented. Agriculture had to be invented. The math and science that we have, even the idea of equal rights, is not found in indigenous cultures. Somebody invented that, and boy, it's a hard idea to learn. And the discouraging thing, perhaps, is that the things that are natural to us don't have any particular correlation with what we call civilization. And these very, very hard to come up with and hard to learn inventions in various ways of new ways of thinking that are not particularly natural to us are things that we tend to think of as being part of the process of trying to put together a civilization. And for my opinion is that what school is about, if we should have school at all, is to try and teach these hard to learn ideas. And in fact, human beings are not only easy to fool, as Shakespeare pointed out, but we love it. We have stories and theater and magic and a whole bunch of other activities that are enormous fun in which we want to be fooled. So we go into situations where we want to suspend our belief in order to have a transcendent experience of some kind. And actually with us today is one of the great teachers in America today, Betty Edwards, who wrote the Drawing on the Right Side of the Brain books. I didn't see Betty, but I'm pretty sure. Hey, there you are. So we learned so much from Betty. And one of the things she does when she teaches drawing is to explain to the class, first thing, that the problems that they're having with drawing don't have anything to do with whether they can move their arms around with a pencil in them. The problems they have with drawing are largely too early perception of the forms out in the world and not enough attention paid to the actual shapes of the forms. So this is an illusion that she uses in which she tells the class, for example, the size and shape of these two tabletops is exactly the same. And everybody says, no, that can't be. And Betty does this with cardboard, but I have expensive digital cardboard here. So she takes one tabletop here and brings it over to the other tabletop and rotates it. And puts it on there like that. And now I've done this hundreds of times, and I still can't see that they're the same size and shape. And neither can you. However, you can satisfy yourself if they are. I don't really have time enough to leave it on much longer, but the way an artist would deal with this situation, an artist is a person, in part, who's willing to admit that they're blind. So if you think about it, you can't learn to see until you admit you're blind. And this applies in science as well. So if you admit you're blind, you say, okay, I'm going to use an instrument And what they do is to measure off the exact subtension of the angle from the eye to the object, and then transfer it over to the other object, and they notice, oh yeah, this is exactly the same length. I just can't see it. My brain can't deal with it directly. And it turns out the whole universe is like that. So if you want to teach somebody about science, a good start is teaching them to draw, because drawing forces the suspension of perception and the attention to the more microscopic details in which many, many interesting things lurk. And another one that's good that if we had more time I'd do, this works very well with oranges. If you take 2 quarters and put one twice as far away as the other, you can see by the diagram here that the farther away quarter compared to the near quarter should look like that. So this quarter should be tiny. But in fact, unless you do this very carefully, what you see is that. The one that's twice as far away is only about 80% the size. And it's fun to actually take the quarters and fix them in place so you can control them exactly. And in fact, you still get that illusion until you exactly close one of the eyes and look very, very carefully with the other eye, and you can start seeing that this one is actually much, much smaller than your brain wants to make out of it. And this is called size constancy, and it's one of the problems that plagues artists, probably for the last 10,000 years. You have to have some way of defeating it. So seeing shouldn't be believing. And that brings us to what school systems want children to learn with regard to science and math. And I'm confining the discussion about understanding here just to science and math for this talk. It's a large subject. Here's, as of last Sunday, and for the previous 10 or 12 years, the standard 1B in the 5th grade science content for California has this interesting sentence. Students know all matter is made of atoms which may combine to form molecules. Now, anybody have a reaction to that? Well, okay. So one question is, what do they mean by know, given that atoms are still controversial 100 years ago? But even more, the people in the physical sciences here will know quite well that science today does not think most matter in the universe is made of atoms. Not even a majority of the matter in the universe is made of atoms. And what's interesting about this standard is this has been pointed out to the state of California for more than a decade. And they have not changed the standard. All they have to do is, they could change matter to elements and get something more like it. But in fact, the reason they won't change it, we found out, is because this standard is taken from a textbook, and they don't want to try to go through the process of changing the textbook. The other way of looking at it is that this standard implies that nothing that is important about science has to be taught to children in order to succeed in teaching science in California. Nothing about what science actually is, nothing about how you do it, nothing about the difference in meaning of the word know. Math is similar. So the overlap of school math with real math is almost non-existent. Perfect example is the idea of invert and multiply. It used to be called cross multiply when I was in school. It's taught to children as a principle to be applied, not as something to be understood. The children don't have enough algebra in 5th grade to do the manipulations that will derive invert and multiply and thus understand what it is and where it came from. And when they do have algebra in 8th grade, this is not revisited because, in simple, the school system absolutely does not care whether the children understand this stuff at all. The math is taught as really as arithmetical calculation using case-based patterns, And science is taught as a new catechism for a secular religion. And both of these are both quite natural, because if you think about how life was 80,000 years ago, we didn't have the grand principles and abstractions and processes. People were trying to find out what would work to keep them alive. And so it's quite natural that the dominant way of dealing with ideas in our brain is like a cookbook full of recipes. And in fact, that is why the children that you saw in the movie could not retrieve the related facts. They were off on a different page of the cookbook, which you could prompt them to get to, but in fact they were not related in any systemic way. And of course, we still do this. Everything is done cookbook style, but now we have additional processes that want to look beyond the simple particulars to try to find if there are unifying forces. And in fact, the Greeks were among the first people on earth to want to reduce the many to the few. And so a longer talk along these lines could pick any or all of these words and talk about how their meaning has changed over the years. The people who invented science, I think, were not worrying about whether reusing old words with new meanings would actually cause confusion. But in fact, I believe that people would have been much better off if they'd simply made up new words. For instance, instead of using knowledge or know over again, make up a different word for it. Instead of using theory over again, make up a different word for it that has the modern meaning attached to it. Now, when I was about 10 or 11, one of my hero was Eratosthenes. And this is an often told story. You'll find it in hundreds of different forms on the internet and in most books on elementary science, about how Eratosthenes, who was the librarian of Alexandria at the time, had heard about a well. Syene here is where Aswan is today, so about 500 miles south. There is a well, and on a particular day of the year, the sunlight would go straight down the well and be reflected back up. And on that day, Eratosthenes stuck a staff in the ground or used the tower of the Alexandria lighthouse to see that the shadow was cast and to look at it in slightly more detail here. The angle he measured was around 7 degrees, and that is about a 50th of a circle. And so multiplying the distance to Aswan, which is 500 miles by 50, gives you about 25,000 miles. And they had a pretty accurate value for pi by then. In 240 BC, Archimedes was about 48 years old. And he had done a good value. And so they were able to get that the Earth was about 8,000 miles in diameter. I just loved this story when I was a kid. And when I was 14, I encountered it again, and all of a sudden I realized, hey, wait a minute. Could that possibly be so? What about this case? What if the Earth is flat and the sun is near and small? Then, of course, the sun will go straight down the well, and of course it will cast my 7 degrees shadow 500 miles away. So why didn't they tell me that in the story? And the answer is it's a story. Stories do not have to be true in order to sound good. That's the problem. In fact, they rarely are true. And in fact, nowhere on the internet could I find this case. This is taught as here's how Eratosthenes did it, but not revealing how it was actually done. So when I was 14 or so, I set off to find, well, how did Eratosthenes actually do it? And I'm going to show you as quickly as I can how this actually happened. So the two things we need to find out is the Earth round or flat? And is the sun near and small or large and far? Aristotle, who lived before Eratosthenes, had remarked that if you're on land, you can see the sails of a ship before you can see the hull. And I think he was a landlubber because mariners actually have crow's nests up on the top, and they know that they're the ones who really care about seeing land. And if you've ever been on a sailing ship, you do not look for land while you're standing on the deck. You get up to the highest possible mast. And the reason is that you get to see further over the horizon. You have a chance of seeing the island where you're trying to go. So that was one indication they had that the Earth might be round and somewhat large. More interesting one was noticed by several people, including another hero of mine, Aristarchus of Samos, and that is if you look carefully at a lunar ellipse, this is where the Earth's shadow is doing something to the moon, you can actually see the curve of the Earth's shadow, indicating, oh, something that we're on, when you put a big sun behind it, is casting a circular shadow. So the Earth is probably round. Then the question is, where is the actual sun? And in order to understand that, we have to look at something that most children, this is one of the areas where most children check out in 5th or 6th grade, because they're told that similar triangles have proportional sides, but they're never given a reason for it. So this is one of those simple elementary things that remains a mystery for most people. One way of looking at this is if you take a triangle and measure it with a particular ruler here, you get 60, 100 by and 80. And then the thing the Greeks realized, one of their greatest inventions, was to realize that the gods don't care what ruler you use. They could not care less. And so if you make a different ruler that is gradated the same way, you can measure off the same distances, 100, 80 here, and 60, and you're essentially creating the same triangle. And because you're creating the same triangle, the angles have to be the same. It is the same triangle. This is one of the great, it's amazing to think of being able to understand this. And once you get this, many other things can help. And now we have this interesting idea of, because we know about similar triangles, we can actually do something really interesting. Simple one to do with a child is to first take a dime and a quarter. Now we're not trying to see if they're the same size. We're trying to find the distance where the dime occludes the quarter. So we get something like this. And if we measure the distance in dimes, it's about 7 dime diameters. And because this large triangle is similar to this one, the distance to the quarter is 7 quarter diameters. And we can do that without having to measure the quarter. That's the key, because you can't go out there and measure the moon. So somebody in Alexandria, maybe Aristarchus, took an Alexandrian coin here and did this with the moon. So a way to do this with your kids is put the thing, when the moon can be seen through a window, scotch tape a dime to the window, and then back up until the dime is exactly including the moon, and then measure that distance, and you'll find it's 110 dimes. And what that means is the moon's distance is 110 times the diameter of the moon. Amazing, is to me. Because these guys are reaching out to a place that they can't go to. So it's 110 away, and we have this little idea here. Let's measure this a little more carefully. So they would do it by drawing a picture. Let's make an Earth here that looks like it fits pretty well. If we measure that carefully, it's about 2.5 times the size of the moon. That helps, right? Because if we could just allow Eratosthenes to do his work, then we'd know how big the Earth is, we'd know how big the moon is, we'd know how far the moon is away. And to give you an idea of what we're looking at here is one of Aristarchus's great ideas. So he said, okay, the sun could be near and small, and what I really want to do is look at this sun as when the moon is actually half full. So I have this relationship. The sun is pointing in this direction. And then if I measure this, this is when the moon and the sun are in the sky at the same time. So if I measure this angle here, I will get some sense of where the sun actually is. And so the angle was not 16 or 18 or 20 or 58 or 63. Aristarchus actually measured 87. So the sun is way the heck out there and large. How do we know it's large? Because the moon occludes it. So the sun has to be 110 sun diameters away. And the actual state of affairs here is this. If you measure it accurately today, it's 89.8 degrees. Way out there, much further than Aristarchus thought. But getting it out there is sufficient to go back and say, okay, let's get rid of that guy. Now we get 25,000 miles around, 8,000 miles in diameter. And because of that, we should be able to start thinking about what the actual size of the moon is. Now, the important thing to realize here is that the sun is not infinitely far away, it's not infinitely large, so the shadows taper, and Aristarchus realized this. So this is out of scale here, because remember the moon is 110 moon diameters away. This helps us see, and here's a blown up picture of it. And notice that the parallel lines that are the size of the Earth and the size of the moon here give us an indication that we should be able to take half of this moon shadow. Notice the moon shadow tapers down to nothing. That's why it occludes the sun. So the angle of that moon shadow just goes perfectly in there. And the angle of the moon shadow goes perfectly in here. And these are complementary angles. And that means this is the same angle as this. And that means I can copy this guy and just flip him over like this and put him in here. Okay? And I can copy this guy and flip him over and put him in here. And we can see that approximately the Earth's shadow tapers 1 moon diameter to produce its image on the moon. And we should worry a little bit about the 4,000 miles of difference here for where the shadow starts. It doesn't go all the way out here. But the real state of affairs is this. Remember, the moon is 110 diameters, and so the 4,000 miles difference here allows us to say, yeah, it's just about 1 moon diameter. And just to give you kind of an example here, if we lay this out, if I put the so right about here. So this is the Earth, and that's actually how far the moon is away. So that's about 110 baseballs away. So it's worthwhile thinking that these scales are bigger than we think. And the angles are much, much smaller than we think. But that allows us to go back and say, okay, we actually have to add 1 moon diameter here. So let's do this calculation again here. Right about like that. And by adding 1 here, we see that it's really 3.5. It's about 2,200 miles in diameter. Let's go back to Aristarchus' diagram of the moon-Earth system. Plug in 2,200 here. And so it's about 240,000 miles away. This is done without telescopes. This is done just by attitude and change of perspective. and constructing a chain of reasoning from the simplest things you can do with tiny physical objects. This is why the triumph of this way of thinking is so astounding, that it can be done at any time in history. It could have been done 100,000 years ago, but nobody thought to do it. Okay, and then, now, the sun is 110 sun diameters away. What does that actually mean? And if we could have the house lights up a little bit. House lights, yeah. So this is a little complicated. Maybe I can get you to hold this. And I had to go from a basketball to this ball because there isn't enough room here. But my friend Ted Taylor over there is going to hold up. And what he's holding up is not the Earth, but the orbit of the moon. The Earth is about 1/100th the size of the sun. So the Earth is actually the size of a pinhead in the center of that, 93 million miles away. See, pixels are not enough for getting an idea of these huge scales. You can't really show it on a screen. Okay, thank you. Just to give you an idea of what we were comparing there is the sun and the Earth is about this size, and this is the orbit of the moon that Ted was holding up there. So we had this interesting thing in history that the Greeks could make fairly accurate. This is actually Eratosthenes' map of the world, another thing that he did. So in 235 BC or so, they had a pretty good sense of the explorable world in a way that was actually useful to people. 1,500 years later, the maps in the Middle Ages were stories again that essentially showed the world as it had to be. That is, the Garden of Eden is right here in the center, and it's very, very hard on these maps to see that this is actually Italy here, and this is Greece, and England is squeezed out here in the corner, and this is Jerusalem here. So these are maps that were made from deduction about what had to be true according to what the beliefs were. A few hundred years later, we start seeing maps looking like Eratosthenes because people were starting to explore the world again, and they needed maps that were not about the way the world had to be. They needed maps that were more like the world actually was. And it was this change into map making that and exploration and maybe even the physical dangers involved that got people thinking again about how to get past our perceptions and how to get past our stories to understand much more about what might actually be there. This is a nice map of India as it was mapped in the 19th century by a series of interlocking triangles, very similar to the way the Greeks mapped the sun, moon, and earth system. And then in our time, we're back a little bit in a story world for most people. This is Tolkien's Middle-earth. And the important thing to realize, it is not possible to look at any of these maps and know without other knowledge whether these maps are depictions of reality or depictions of stories. So maps are just stories, and whether a map is useful for an explorer or not depends on the science involved, that is the relationship to the real world. And in the 18th century, people carried around little globes in their pocket that when they were having coffee, they would take the globes out and they could see what the world would look like from space. 200 years later, we went out there and took a picture, and it looked very, very much like what the 18th century thought. So science is like that. It's kind of a way in which the maps it makes are never entirely accurate, but the important things about the maps are that we understand quite a bit more about what the inaccuracies are about. And so we don't have to completely understand in the biblical sense of truth and falsity what molecules and atoms are in order to make insulin to save a 12-year-old's life who has infant onset diabetes. So the triumph of science is by giving up old ideas about truth and falsity, it actually finds a way of splitting false into 1,000 varieties of false, some of which are incredibly useful and important. Now, just to give you a glimpse of how this relates to children, probably the most astounding thing to many adults, particularly when they consider what is actually being done in most schools, is how capable young children are. So here's an example of a very unusual teacher with 6-year-olds, and she did, these are after they've been in her classroom for about 3 or 4 months. And this teacher was an unusual first grade teacher in that she had a very, very strong feeling for mathematics. She loved math, she thought math, she was a mathematician, and she loved first graders and kindergartners. So the idea here is pick a shape that you like and make the next larger shape just out of those shapes, and make the next larger shape and make the next larger shape. You can see trapezoids are somewhat challenging. You have to twist them around. So the kids all do this independently. Then one of the things this teacher did is kind of interesting, is to treat mathematics in this grade as an empirical science. So the kids are making artifacts. They make the artifacts, and then they look to see what they did. So, and they do this by not using the tiles directly, but making a representation of what they did. So here's the diamonds made out of cardboard now. Then they look to see what is actually happening in the process when they did this. And here's 6-year-old Lauren said, okay, the first one took 1 tile, and there were a total number of 1. Next one took 3 more tiles, and there were a total number of 4. The next one took 5 more tiles, and there were a total number of 9, 7, 16, and up to about 25 or maybe 36, the child could see that, well, these are all the odd numbers, so I'm just adding 2 to get from here, and these are the square numbers. Probably not sure about 7 times 7 at this age, but these are the square numbers, and the progression here is incremental. We build on the thing that we had before. And then the teacher had all of the children bring their projects up to the front of the class and put them on the floor, and everybody went, or at least I did, holy shit. Because they suddenly realized that the shapes were different, but the growth law was exactly the same. Every child had made a table like this, and they realized that what they had discovered was a way of making things larger out of things in a progressive way, and the materials that you used were used in a very, very simple way. This whole thing can be generated simply by taking the number that's here, adding 2 to it, get that, and then add these 2 to get this one, add 2 to it, and so forth. Just keep on adding your way down, and the scientists and mathematicians in the crowd will recognize this as a first-order discrete differential equation, and they'll recognize this as a second-order discrete. And the people who like physical science here will realize that an enormous amount of physical science is just handled by this kind of math. And this is a form of calculus that doesn't involve continuous functions, and it's a form that children can actually deal with. So what does this mean? So an example of what children do is to essentially make toys, things that they like to do on the computer, and they play with these toys. They can make these toys do things, and so for example, they will draw a little car here. Just do this quickly. Put some wheels on it. And so far it's just a picture, but this picture can have properties. For instance, it has a, let's call it car here. So one of the properties here is where is it pointing? It's pointing due north now, but if I change this number over here, you can see it counting up and the car is turning. If I turn the number here, those numbers will change. Here's a behavior, go forward. Here's another behavior, turn. If I want to combine those, I can write a little compound expression here that combines these guys and click on the clock and get it going. And to see what it's doing, I can actually drop a pen down, because these are logo turtles in disguise. And so we see it's actually drawing a circle here. And in fact, I can change this. So if I change the angle of turn here to make it something like 3, kids always wonder, is this going to spiral? But in fact, if you think about it, if the numbers stay constant, then it will have constant curvature. And circles are all of the things that have constant curvature, so you're always going to get circles. Okay, another interesting idea is, how can I make my car go down the middle of the road? Here's a script done by these two kids. The idea is that I'm going to ask whether this blue guy sees the road. If so, I'm going to go forward. If I see one curb, I'm going to turn in. If I see the other curb, the yellow color, I'm going to turn out. And so you get something like this. And notice this can deal with very sharp curves because it does not go forward until it makes the turn. So they made a little robot car using the principle of feedback, which is found both in human technology and in nature. So this is the kind of math that these kids do. So I'm going to need some sound here. Here's Jenny, who had an artistic temperament but was also a terrific mathematician.
I did something different from cars racing. Instead, I made pigs racing.
And they're off.
Here we go for the annual pig race. It looks like it's a rough time today. The pink pig crashing into the wall. I have a watcher here that tells me what speed they're going. Oh, and the blue pig's coming in the lead. I have my own pig. I named it Jackson. And usually it loses. But oh look, the black pig is catching up, leaving the white pig in the dirt.
So one of the neat things she did was, how do you keep the pigs in the lane? Well, you saw previously kind of how they did it. And she thought, I can use the nostrils, the colors of the nostrils on my pigs to sense whether I'm going to go out of the lane or not and turn back in. So that's how. So that was fun for them to do. And then the idea is to think about, well, what is it that we just did? So if we look at this, where the car's speed is always going to be 30, and we're going to increase our horizontal position by whatever the car's speed is. If we let it go, we get something that looks like this. So it's dropping little dots, and we can see these dots are evenly spaced. They're 30 apart. And that's a way of thinking about what velocity means looked at in the history. Another thing I could do is to, for example, put a random tile in there. I'll generate some random numbers, maybe from 0 to 40, and see what that looks like. And of course, this is more fun for races, because it's not clear how these are going to generate out, and so you get some uncertainty in what's actually going on. And another thing I could do here is to try increasing the car's speed by something. Let's suppose I increase the car's speed by 15. So each time now the car's speed is going to count up by 15, and I'm going to go that distance. And we set that off, we get a pattern that looks like this. Takes off really fast. So this is a pattern that we associate with acceleration. And the children learn their ideas about velocity and acceleration by playing with the computer. And then the question is, what do these things mean in the out in the outside world? So I want to finish by just showing you a science experiment done by 5th graders. And this is about the 400th anniversary of this. Galileo did this about 400 years ago.
And the objects that you think will fall to the earth at the same time. Both hands. Oh, do not pay any attention to
Now,
what
common sense
anybody else
says
is
that the
doing.
heavier ones are going to fall faster. So we first use stopwatches.
Who's got the apple?
The stopwatches really don't work. When did he let it go? When did it actually hit?
We're going to the classroom.
The 0.99 seconds.
Together. So put sponge ball.
Okay. I think we should do the shot put and the sponge ball because they're two totally different weights. And if you drop them at the same time, maybe they'll drop at the same speed.
Drop.
Yeah, so we found that in every class of about 30 children, there'll be one Galileo child. That's an interesting ratio. So the estimate of scientific literacy in the United States, not just counting scientists, but people who are scientifically literate, is about 5%. So that says you should find one Galileo child in each class of about 30. And so she just cut to the chase, realizing, hey, forget about measuring it. We're interested in the result, and we can listen for the result, just as Galileo did. But if you want to look at it closer, today we have inexpensive handheld video cameras, and so we can actually take a video of what actually happened, and we see right away that even single stepping it, it's kind of hard to see what's going on, but we can extract the frames from the film. This is every 5th frame from the video, and we can even stack them up. And as soon as the kids see this, what do you think they say? Acceleration. What kind of acceleration? Well, let's measure. So one of the ways of measuring is taking these translucent rectangles and adjusting the height of the rectangle so they're measuring from the bottom of one ball to the bottom of the next ball. So this is kind of what they do. It's hard to do it really accurately when I'm giving a talk, and this is kind of what they do. And then you have this nice thing where you don't have to do arithmetic. You can do it geometrically by just stacking up these guys. And just a little thought says, okay, each one of the heights of these things is the velocity in that time interval. And what I'm seeing here is the difference between one time interval to the next, and that difference looks equal. And remember what the first graders did? Difference there was 2. Here the difference is minus 4.7, so you make a simulated ball. Do the same program that we had with the car just a few months ago there. But how do we know that we actually are looking at nature? So let's take a look at what Tyrone did here.
And to make sure that I was doing it just right, I got a magnifier, which would help me figure out if the size was just right. After I'd done that, I would go and click on the little basic category button, and then a little menu would pop up, and one of the categories would be geometry, so I click on that. And here it has many things that have to do with the size and shape of the rectangle. So I would see what the height is. And I kept going along the process until I had them all lined up with their height. I subtracted the smaller one's height from the bigger one to see if there was a kind of pattern anywhere that could help me, and my best guess worked. So in order to show that it was working, I decided to leave a dot copy so that it would show that the ball was going at the exact right speed and acceleration.
Is that cool? So anybody who doesn't have tears in their eyes right now, you don't understand what's going on, because 70% of college students fail to understand this particular set of ideas. Part of it is because the math that they're portrayed in college and in high school is not the best form of math for thinking this way. This is a better way of thinking about it. But part of it is because this is not an easy thing to do, and yet the fifth graders, because they have a much more appropriate form of math in which to think, have plenty of brain power to do this. Lily McDermott here is a physicist at the University of Washington who has studied high schoolers and college students for more than 25 years and their difficulties in learning these new ways of thinking about the world that were invented just a few hundred years ago. So when we think about education in the 21st century, we have to pay heed to two important things. One is that it's not just the way it was 80,000 years ago. And trying to teach things as they were taught 1,000 years ago or 500 years ago may not be appropriate. If we want children to understand them, we have to heed the fact that children's minds are set up differently than adults, but they're no less able than adults. They just think differently. So we have to find the frameworks that the children can think in, and the children, in fact, can learn a form of calculus that allows these ways of thinking about them, Newtonian dynamics of various kinds, to be dealt with in a way that most college students can't today. The key to this is that the computer is happy to add up millions and millions of little quantities. And so much of the thinking here in this different form of calculus can be done looking directly at the differential equations in their discrete form and simply thinking of what's going on as incremental addition, which in fact seems to be the way the real world handles most of these things. This changes tremendously the kinds of things that we can hope to do with children, and it also opens the door for thinking that children might grow up to think in a very, very different set of ways in addition to the normal ways that their brain is bringing about. So maybe the next time you think about technology, think about it perhaps not as just all the practical things it can do for you, but think about technology as a kind of an amplifier that, when used properly, these amplifiers make us much, much smarter than we seem to be. And in fact, the difference between the kinds of things we can do and the kinds of things that were done 20,000 years ago is not in a change in IQ, as far as anybody can tell. It's actually in a change of perspective and a change of point of view that allows us to think in a new way. Thank you very much. Okay.
In this Kyoto Marathon that our awardees are entered in, the next event that Alan has is a lecture at the Rotary Club downtown at noon. So we are limited to just a couple of minutes for questions. Could we have the house lights up, please? Thank you. A couple of minutes for questions. Do we have some? Yes?
How things are taught now and how what tremendous changes are going to require to adopt your...
Yeah, I mean, of course, that's always the interesting question. And ever since Montessori, a lot has been known about how to deal with children differently and to get tremendous changes compared to ordinary schooling. And the plea I usually make at the end of a talk, and I certainly will at the Rotary thing, is that in many ways the prime need is to help the helpers. So we have many people who have dedicated their lives to helping children, but because they are embedded in the same system that doesn't teach this stuff. Most of the people that are helping the children are not invested in these other ways of thinking, and so you get this rather long, drawn-out, seemingly conservative approach. So the ideas change much faster than the system's ability to take them up. But there are a couple of approaches to it. One of the most important things, something that we have tried a couple of times, haven't quite found the right place, is that just like you need to start earlier with the children, why not start earlier with the teachers? If you want to find a busy person, look at a teacher in a classroom. Then ask yourself how they're going to learn something that is even more foreign than a foreign language while they're doing all this other stuff. So maybe a better place to do it is to at least go to the teachers' colleges. Maybe a school district could give preferential hiring to the teachers in the teacher college who have been willing to go through a special program to learn this stuff. But again, the printing revolution in many ways certainly was a big factor in the Reformation, certainly was a big factor in the 16th century, but the full power of what the printing press catalyzed is seen in the 17th century. Now is about 150 years after the technology was actually introduced into Europe. So this is not unusual for these long lags. As soon as you can get a larger percentage of children who understand this stuff, some of them will become teachers, and immediately it starts working. So one way of short-circuiting the process is do peer teaching. 5th graders and 7th graders love to help 2nd graders. This has been studied quite a bit. Why not do much more of that? Why not do more things over the internet? Why not do more things in after-school programs where you don't have to worry about state legislatures and random ideas about education and so forth? There's a lot of things that need to be done, and basically the parents and the concerned citizens of a community can make the change in spite of the difficulties in the state and the nation about this stuff. Some place just has to make a stand, and the idea would be to pick a place that's large enough to have, for instance, like here, that has a major source of teachers who, most of which wind up in the school system here. That is a recipe for success. So that's one set of ideas. But the other way of looking at it is I've been doing this for more than 35 years, and it is not easy, for instance, even convincing the National Council of Teachers of Mathematics that this is mathematics. Because unfortunately, the NCTM is not full of mathematicians, it's full of math teachers, which is absolutely not the same thing. Yes?
It's not just attacking mathematics, attacking physics. The dean knows what I do. I'm the guy who sent you lots of emails you've heard about. There's a fellow named John Bradshaw. You know about 12-step programs. He was big in the late 80s.
Yeah.
Bradshaw in the field. He talks about the dysfunctionality. There's someone else who does it, Brian Martin, Wollongong University, failed physicist from the U.S. who went to Australia, about the whites-only country club, as an example, circling the wagon trains to keep out the heathens, make the heathen, and of course, no doubt, not as good as us in the crowd that made the wagon train. What the wagons? It's a jargon. In mathematics or in physics, I'm a physicist, or in biology, that literally obfuscates any understanding of an outsider. It's just like a church that keeps out the...
Yeah, I couldn't agree more. And for instance, just a good one of many candidates to bypass is trig, because what's important about trig can be done just by thinking about triangles, and you really don't need all of the jargon of trig when you're doing the formation. Any other questions? No more. No more? Okay. Thank you.
That was wonderful, Alan.
Great.
Thank you so much. I need to wrap up for a moment. Thank you for sharing your insights with us, Alan. I would like to express our university's thanks to the Inamori Foundation, to Inamori Sensei, for their continued support of San Diego State University and for the to the San Diego community. To the representatives of University of San Diego, UCSD, and our representatives from our sister institutions in Mexico. And finally, thanks to the members of the Kyoto Laureate Symposium Planning Committee, the San Diego State University Planning Committee, Kaneko Bishop, and all the volunteers who provided their expertise and support. There are SDSU volunteers waiting outside the lecture theater to escort you back to your cars if you came in one. Thank you very much for joining us this morning.